Okay, I'm David Greenwood from Newcastle University, and I'm here to present paper 454, which is a very short to medium term demand and generation forecast, a case study in Austria. This work was led by my colleague Marcos Santos, and it's part of the Merlon project, which is an EU project looking at local energy systems for improving security of supply and improving the economic opportunities of renewable generators and other distributed energy resources in those systems. So within the Merlon project, we need forecasting for a few different reasons. So the first thing is we need to be able to balance supply and demand. We need to be able to dispatch different flexible assets, and we need to be able to keep the system in balance in the event that we want to run the system as an energy island rather than as a part of the wider network. And on both the trial sites for Merlon, so this work focuses on the Austrian pilot site, but there's also a Spanish pilot site. There's a large amount of renewable generation, which we need to be able to match to the demand and make sure that we're making the best use of it, and also getting the best value out of it based on varying energy prices. So what we're doing here is we're forecasting both the generation and the demand, and we're doing it in a way where we quantify what the uncertainties look like so that we can then deal with those inside the scheduling process. And the scheduling process is available as another poster within the conference. So the forecast methodology we've chosen to use is based on artificial neural networks. So artificial neural networks can extract patterns and knowledge from complex data, and the way this has been implemented, we can automatically retrain the models if the patterns in the underlying demand change. So this was important last year because we were building these models and kind of testing them during the pandemic. And obviously, if everyone's suddenly working from home, the demand, which we're going to see on the electricity system, changes significantly. And so our model allows us to update that. And in fact, probably going forwards, all of our demand data is going to change and won't be like it was before the pandemic started. So just on the right hand side of the slide, you can see a few examples of the forecast output. So this forecast model performs extremely well. It has a mean absolute error of a few percent if it's forecasting up to kind of 3 days ahead, which is very good. And for the next half hour, it's very accurate. The demand forecast is more accurate, I think, than the generation forecast, simply because the demand is following a much more reproducible pattern, whereas the generation forecast, while there are elements of it that we can predict, some of it is quite stochastic and down to, for example, cloud cover, which would require very complex forecasting that was beyond the scope of what we were implementing for this project. And then on the bottom right, we can just see what happens when the demand changes with the lockdown. So this is showing the forecast for the first few weeks after the lockdown, using different amounts of data from in the lockdown to do the forecasting. So what we see is if we use our pre-lockdown model to forecast the demand in the lockdown, we get a very high mean absolute error, so 14.6%. But as we start to have 2 or 6 weeks of demand data included that is from the lockdown period, we see that performance improve quite quickly. Okay, if you're interested in the project at large, I definitely recommend you look at our other paper, which is number 385. Okay, thank you very much.